Hi everyone, welcome to the tutorial on flow through an orifice. Previously, we already saw how to develop a flow measuring device, right? We already have idea about Venturi meter that we already calculated and calibrated in the last tutorial. So today I'll talk about this orifice. So what is orifice? You can see a picture right here, that one. So basically orifice is an opening. It is basically an opening on the way of a fluid flow, and if we have this opening, and by taking some measurement we can even measure the flow rate. If we have a reservoir and if we just make a hole, right, make a hole, then flow will come out, and then we'll take some measurement, and then we'll be able to measure the flow rate. So that's the benefit of orifice. So in definition, it is nothing but it's an opening, right, in the wall of a reservoir or a tank. So that should be perpendicular to the direction of the flow. For example, we have a tank here, this one, this is the tank. And then we have that opening here, and water is flowing, right? We have opening and it is pretty sharp, that is pretty sharp. And water is flowing that way. And see what is converging, that's the streamlines. So these are the streamlines that are converging. And see, converging, and then it is just flowing through this hole, and after that still it is converging, it is still continuing. See, it's continuing to converge, and at some point it is even more converged than this opening. It is converged here. And what is actually happening, the cross-sectional area, if we know the diameter of this opening, we can calculate the cross-sectional area. But cross-sectional area at xy, this section, that is less than the cross-sectional area of this one. That's why streamlines are converging, and we have a location where the cross-sectional area of the jet is minimum. And then after that, it is even started to diverge. So we know this behavior of a of an orifice. If you open a hole, and then if you allow the water to flow through this opening, then it will flow like this way. It will converge, and then it will diverge. So that location, xy plane, here we can see that is called vena contracta. We'll see that is called vena contracta when the vena contracta. Okay. So why is that? Because contraction is happening here at this point, xy section. So that's why it's called vena contracta, and that is the special property of this orifice meter, right? So this is another practical application of Bernoulli's principle. We saw, right? We saw, and we'll see even another 2 or 3 experiments where we are going to apply this Bernoulli's principle for measuring flow rate. So these are the applications. So today we'll also calibrate this device, and this is pretty simple. So what is the practical application of this special orifice meter? So if we have any tank, means a reservoir, then we can measure the flow. And if you want to control the head of a reservoir, and we can use orifice meter to measure the flow rate, and we can control the overhead, right? Since that is the tank, and if you want to maintain head here, then what we can do, we can allow, right, water flow through an orifice, and then we can control that head, this head. We can maintain a constant head using this orifice. So that is the practical application, and we can measure how much flow is happening here. So you can see the practical application, and then we can see the setup here. So if we have overhead tank like this one, or a tank, it may be square or it may be circular, whatever it is, it depends on the experimental setup and the availability of the instrument in your laboratory. So if we have a water like this, and if we have an opening, right, and then what will happen? Water will flow like this. That is the jet, right? It is flowing like a projectile. So we'll apply exactly the same principle that we apply for project, right, for projectile, and we'll calculate the actual velocity and where the point of hit, right, the point of action and the point of hitting, right, we'll calculate that distance and the velocity. So that is the practical setup. It depends on your laboratory, and let me just quickly derive the equation, right? So for our setup, we are gonna see a generalized version of this setup. So irrespective of the tank size, whether it is circular or a rectangular tank, whatever it is, the main principle is same. If you follow the main principle, it's easy to follow, okay? So we have a section of a tank or an orifice right this way, and we have a head, right? We can see here the H, that is the height from this opening, and we have opening here, and the wall of the tank. The wall of the tank is this, then we have we made it sharp, right? It should be sharp. Why? Because if we have a circular, this one, if the section is that, then if water flows through this hole, then definitely water will touch this one, and then we'll have more friction loss. Other than doing this, if we make this, right, this point as very sharp, then we'll have only one line of contact. Then we'll have less frictional loss from this thicker opening to the sharp, right? So that's why we made it very sharp, so that the water can touch only one line, and then we can minimize that frictional loss. So that's why it is sharp. And we know the diameter. If you know the diameter of this D, and since it is circular, then we can easily calculate the area, right? Area, what is the equation? Pi over 4 and D squared. So we can calculate that. So let me just explain the setup. So we can consider that's the opening, and that is the center of the opening, baseline. And what actually we have, we need basically this H, because that is the opening from the center of the opening, and that is the H. We have water basically when we're allowing water through this orifice meter, then we have head, right? That is the head over this opening. But what we actually have, we can't even measure this H directly, because this experimental setup that we have here, we have a setup that has this lower H or smaller H outside of the tank. This is the piezometer. It is installed, and the piezometer starts from this level. So that's why we have to measure this difference, right? This difference is called head correction. If you know this H, right, we can measure this one. We know that for this setup H prime, and we have to calculate that H because we need this one. So it will be H minus H prime. Okay, so that is because of the setup. But for your laboratory setup, maybe it is directly, maybe this should be locating from here. Then we can use this one as equal to this one, whatever it is. But we have to measure this capital H, this one. That should be just from the center of the opening or orifice to the top of the tank. So that's the condition, okay? So if we have that, so there will be nothing else we can do. But for this setup, we have setup like this. We have H here, and we have a head correction H prime. That's why we need to deduce that head correction to get this total head or the actual head that we have over this opening. So let me just derive the equation. It's pretty simple equation for orifice. So we'll apply the Bernoulli's principle, because that is the application of Bernoulli's principle. What we're going to do here, we're considering that point, this one, okay? That point, it is point A. We're going to apply, and we have another point at the top of the water, this point B. So we're going to apply Bernoulli's principle in between this point. So what will happen, right? So you know Bernoulli's principle, because that I'm assuming that that is my reference point. That is my reference point, okay? Datum or reference. So that's why we don't need to apply any elevation head. We don't need to add any elevation head, because that is the reference line I'm assigning here. So you have to only add the pressure head and the velocity head. So for point A, do we have any elevation? No, it is located at the datum, right? So there will be no elevation head. And what will happen? Is there any pressure head, or is there any velocity head? Right? Yeah, definitely we have velocity. And we, right? Do we have any velocity? Yes, of course, but we don't know the velocity. We'll know the velocity. What will be the velocity? So it will be 0 plus v square over twice g and equal to, for this case, do we have any velocity? No. What we only have? We have that height, right? That h, only that h, the head we have, right? The pressure head we have there. So that's that. We don't have anything. The velocity is 0. So from this relationship, that is the theoretical, because we applied theory here and we are getting this. So that's the theoretical velocity to gh. Since we know the velocity, if you want to know how much flow is happening through this opening, so qt will be a and that vt. So what is a? A is this one, area of the opening, right? So you can calculate that. Means a root over 2 g and h. So for a certain opening, for a certain orifice meter, so the diameter is constant, so the area will be constant, and we know that root over 2g, it is also constant, so the whole amount is constant. So what we can do, we can write qt is equal to k, right? We can write this one k and h to the power half again, because we know how to write this equation. We saw that, right, in Venturi meter. Then we can calculate the efficiency as before, the coefficient of discharge. How can we calculate that? CD, right? If we somehow know this A actual discharge and we know this theoretical discharge that we have just from this equation, then we can calculate CD, coefficient of discharge, means how much flow is happening actually. How can we calculate that? We have a setup, right? We'll measure the way we measured before, right? So here we have a tank. We know the size, right? 30.5 into 45 centimeter by centimeter. Then we'll allow, right, 10 centimeter of water. Then we'll have the volume and we'll measure the time, how much time will take to have a depth of 10 centimeter for this 30.5 into 45 size of the tank. And then we can calculate that QA as before, V, right, water, and divided by T. So actually we can calculate that flow rate, and theoretically we can calculate that flow rate, and we'll have that coefficient of discharge, and we can see the efficiency. It should be less than 1 definitely. So if we want to calibrate this device as before, we can write the same equation, QT and CD, and then we can write that actual equation, A root over 2g and h to the power half, right? And this is basically constant, as we just mentioned. So we can write C and h to the power n and QA. So that is the general equation I just formed. And see, since the theoretical exponent is 0.5, so for measuring actual flow rate, this may not be 0.5. This should be close to 0.5. So we don't know the value for this device. We have to just conduct experiment for different flow rate, and we can measure the actual flow rate, right, as before, and then we can plot. So since these are non-linear relationship in between that QA and H actual head, so we have to plot on a log graph paper as before, right? And then we have to calculate the slope of the graph, a slope of the straight line. Then we'll have the value of n, and then from that graph we can select another point, and we can validate this equation to calculate C as before. I'll show you again today, and we'll repeat this process every day. Okay, we'll repeat that every day. We'll repeat this, no problem. So that is the equation we have to calibrate for velocity. And there is another one, that is one coefficient of discharge, and there is another coefficient of contraction, CC, coefficient of contraction. It is what? It is basically A naught and A. What is A? A is the area of the opening here from this one. And what is A naught? A naught is the area at the vena contracta, So if we measure this distance, that is 0.5 d from this opening, and d is the opening. If you know the diameter of the opening, you know that the location of the vena contracta, it is located 0.5 d from the opening to the right side, right? But you don't know how to measure this diameter, the diameter of the jet. Then we can calculate A naught, right? We can't do that, but we have to calculate that area at the vena contracta. So we can do that A naught and CC into A. But in order to calculate that area at the vena contracta, we need to calculate that CC. So there is a relationship. There is a relationship in between coefficient of discharge is equal to coefficient of contraction and coefficient of velocity, CV. So what is CV? It is called coefficient of velocity. So what is the actual velocity of the jet and what is the theoretical velocity of the jet? So theoretical velocity of the jet is this one, you know, right? From the theory, Vt is equal to this one. So CV is nothing but Ca divided by Va divided by Vt. But we know Vt from this equation, but we have to calculate Va. So for calculating that actual velocity of the jet, so we'll apply the same principle that we apply for projectile, right? So then we can calculate CV and we can apply this equation because we know CD and we'll know CV, and from this equation we'll calculate CC, and we'll just put CC here, and we know the area of the orifice because we know the diameter. Then we can calculate the area of the vena contracta. So this is how we'll go, right? We'll move forward. So let's calculate the area of the vena contracta after calculating the actual velocity. So how can we calculate actual velocity? So that is the image you can see. What we are considering here, water is flowing, right? And we are assuming that at some point or at time t, the streamline or one particle is here. It was here, and at time t, it is there. So from this vena contracta, we are assuming, okay, that C section, that is the origin, and we are measuring distance from there. And we see that is the horizontal distance x, and that is the vertical because this is the axis, so that is the vertical. It is vertically downward. It is right. If you just throw anything from a plane, from an airplane, what you can do, an airplane will drop something, right, that will fall this way. So that is another, right, that is another equation for projectile, and there is another form of projectile. You can throw anything like this way. So that is another dynamics. Okay, so here we are considering streamline is flowing like a projectile, and at time t, the particle is here. Okay, particle is here. So what will be the value of x if you know the, and what is actually flowing with actual velocity, not theoretical, right? We'll get the water here at certain point of time, and we can calculate x. We know x is equal to VAT at time t, right? So we can calculate VA x divided by t. And yeah, if you want to calculate the time, it is very difficult to calculate, right? And we don't know which particle is coming from this point to that point. That is very difficult. That's why we will try to nullify that time t, so that we don't make any mess up there. So we can calculate even y. How can we calculate y? Because it is starting from this 0. So y is equal to half of g and t square. So we can replace this t with that one. So t, right? So what will be the value of t? We can simplify. So we have t is not t, basically from this equation we can replace. So VA is, we can square, right? V square and x square and t square. So from this equation we can calculate the value of t. So it will be 2y divided by g. Okay, and that's why we can replace the value of a squared. So it will be square and t squared. So it is 2y divided by g, right? So what will happen is va square is equal to gx square divided by 2y. And if you want to calculate va, it will be nothing but gx square divided by 2y. So that is the equation of actual velocity. So we can measure, right? Since what is flowing, and you can measure this x, right? You can measure the x using our scale, because what is like this one. So if I want to show you again, see, you can see the streamline. See, it is flowing, right? The streamline is this one. You can clearly see the streamline, that one, that blue, and it is hitting a point. We can measure why it is hitting. We can easily calculate the x, and we can calculate y by using a scale. We don't need to measure time for catching any particle or tracing any particle. We don't need that. So that's why it's pretty easy to calculate VA using that formula. That's right, this one. So if once we have that VA and VT, then we can calculate that coefficient of velocity CV by using VA divided by VT. Once we have that CV, then we know the relationship CD is equal to CC into CV, and we can calculate CC using that CD divided by CV. And once we have CC, we can calculate the area, right, at the vena contracta, CC into A. So this is how we can, this is basically back calculation. So we can calculate the area at the vena contracta. So there are three types of coefficient here. Coefficient of velocity, it is the coefficient of velocity is the ratio of the actual coefficient of discharge at first. It is the ratio of the actual discharge to the theoretical discharge. Coefficient of velocity, right? It's the ratio of the actual velocity to the theoretical velocity. And coefficient of contraction, CC, it's the ratio of the area at vena contracta to the ratio of the orifice or the opening. So these are the three coefficients we'll calculate in this experiment, right? So what do we have to measure? We have to measure this h, but directly we can't measure h. We can measure this h, and we know the head correction, and we can deduce this head correction from that small h, and then we can get the actual now head. So we have to measure this actual head, and we have to measure the total time for filling up this tank with 10 centimeter. We have to measure this x and y. So these are the readings, and then we'll repeat this for different groups and different flow conditions. Then we'll get the expected values of, then we can calibrate. So for this experiment, what we'll do again, we'll even calibrate this velocity equation for actual velocity, right? So the actual velocity, the equation will be VA is equal to what? We know that, right? CV into VT, and we know CV, V2 is root over 2G and a to the power half. If we just put it outside of this square root, then this is constant, right? So we can apply another basically C1 and a to the power m. So VA will be this. So even we can calibrate the equation for actual velocity, C1 and a to the power m. If we have, right, several values of actual velocity and several values of actual head that we already have, right, and we can plot using that log graph paper, right? Similarly, how can we do that? We can take log, right? Log of VA is equal to, similarly we did log C1 plus m log h. So this is similar to y is equal to c plus mx. So you know the form, right, of a equation that is a straight line. That is the equation y is equal to mx plus c. So that is the intercept of y-axis, that is called c, and that would be x-axis, and that would be y-axis. So then we can calculate the slope. So this slope is this slope, right? And then we can calculate the value of C1 as well. So we already have idea about how to do this. So today we'll repeat again. So let's see the data sheet and let's calculate the unknowns we have. So this is the data sheet you can see here, right? If you see clearly, it's this data sheet, and we need to calculate these unknowns. So the same tank we are using, the area 45 into this one, and the diameter of the orifice is 0.5 inch or 1.27 centimeters. So what will be the area of the orifice, right? We know the area of the orifice will be A is equal to pi over 4 into d squared. So if I calculate that, right? So what will be the value? Pi over 4 into a 1.27 and then square. So let me just calculate using my calculator. 3.1416 divided by 4 and then 1.27 in a square. So what? Okay, wait, just 3.1416 divided by 4 multiplied by 1.27 and a square. Okay, so we are getting 1.266. Okay, 1.267 centimeter square. Okay, and then we have head correction. That head correction we have, it is from the experimental setup, so we don't have to be worried about. If you don't have any head correction for your setup, you don't need that. So it is 9.435. So what we have, these are the bold, this initial, we have the initial measurement of the tank, and because when we are measuring that, right, we have the tank, we have opening here, so we have that orifice, we have that measuring piezometer. So when flow is happening, right, water is flowing through this one, so this head may change, right? What we need to do, we need to have a continuous supply of water to make this head constant, but that supply may not be the same as this flow rate. So that's why this head may be changing. So what we'll do, while measuring that x, while it is just flowing, measuring that x, and for that time for which we are collecting water for 10 centimeter. So within this time period, we'll take this reading once and we'll take the reading again, so that we can take an average to make this accurate. So that's why at the beginning we have 84.5 and at the end we have 84.4. So we are just taking the mean of these two. And for this one, this tank, the initial gauge is 0 and the final gauge is, these are all in centimeter. Okay, all in centimeter. So difference is 10 centimeter. The point gauge, we put a point gauge here, and then at the final stage, point gauge is here. So for 10 centimeter of depth of water in that tank of 30.5 into 45 centimeter, so we'll take the time, and the time is 40 seconds. So what will be the volume of water as before? The volume of water is nothing but 45 into 30.5 into 10, right? It's same as before. So 13, it will be 13725 this centimeter cube. And what is the actual head? Because we know the total head 84.80, right? The head, actual head, it is h minus h prime. So we know it is 84.45 minus head correction. What is head correction? 9.435. So that's that. So 84.45 minus 9.435. So we have actual head 75.015. Okay. Then what will be the actual discharge? It is nothing but the V, right? It is V over T. And what is V? 13 is 13725 divided by 40. So that's that. 343.125. That's centimeter cube per second. That is the actual flow rate. And what will be the theoretical flow rate? Theoretical flow rate is nothing but QT is equal to root over 2G, right? And we have to have A here, and let me just make it here qt is equal to a root over 2g and h to the power half. So we know the area, right? We know the area is 1.267, and we know that 2 into 981 in centimeter per second square, and we know the total head, right? It is 80, that is h basically, actual head. It is 84 point, not after correcting the head, that is not the one I need to do. That should be actual one. So that is the actual head. We have 75.015 to the power half. Okay. Then if we just calculate this one, what will happen? So it is a 1.2667 into square root of 2 into 9.81, not 9.81, 981. If we multiply it with 100, and then out of this square root, we'll have that 75.015, right, to the power 0.5. So what we are getting here, 485.96. So 485.96. So what will be the CD? CD will be the ratio of QA and QT. So 343.125 divided by this, and we are getting C 0.706. So that is the CD. The efficiency is not that high, right? It is 70% efficiency we have. So let's move. And here for the next table, we have, see, the x coordinate is 70 centimeter and the y coordinate is 17. And what will be the actual velocity? We know the equation of the actual velocity, and from that we'll calculate. Okay. So equation of actual velocity, we see VA is equal to root over, it may be your zx square, right, divided by 2y. Let me just check for surety, otherwise it may be. So that's what is the equation I wrote, gx square divided by 2y, and that is the square root. Okay, so we are good to go, right? We have everything. G 981, we know x and x square divided by 2 into 17, and what will be the value of actual velocity? It is nothing but 981 into 70 square and divided by 2 and divided by 17 and square root of all of this. See, the velocity is 376 centimeter per second. So it's pretty high. It is 3.76 meter per second. It's too high. Okay, since it is orifice, definitely flow will be too high. So 376 VA. And what is VT? Right, VT is equal to root over 2G and H, right? We know that. So if we calculate this using that H we just saw, that is a square root of 2 into 981 into 75.015. Okay, so we have a 383.64 this centimeter per second. So what will be the CV? CV will be 376 divided by this value of, and CV is 0.98. See, it's pretty high. CV is pretty high. So what will be the head loss? So we have specific equation for head loss. That head loss HL is nothing but it is given 1 minus CV square into H. So that is the equation for head loss. It is given in the book. We can directly use that formula and we can calculate head loss. So 1 minus CV 0.98 and squared, and then the actual head. It is a certain percentage of actual head. So that's why it is this way, 75.015. So square of this one, 1 minus this, and this will be multiplied by 75.015. So that is the head loss, 2.95 centimeter. Okay, so 2.95 centimeter. These are all centimeter per second. Okay, so we have that table filled up. So if we repeat this experiment for some other groups, then we'll have this value. We have 5 different groups, and we already filled up. We calculated the actual flow rate. We have theoretical, and we have actual velocity and theoretical velocity, and then we have the actual head. So what we will do now, we'll calibrate, right, in terms of actual discharge, and we'll also calibrate for this equation. So we need to plot, right? We have actual, right? We have that information here in this table, and we know how to plot in a log-log graph paper because we saw the formula. So this is the log-log graph paper we saw as before, and what I'm going to do here, I plotted this here already. I have this plot. I'll show you this calculation. I have that plot. We have actual head along x-axis, and we have actual flow rate along y-axis. And I just made one, right? I draw one average line, that blue line you can see, and out of this blue line, I'm reading 2 different points, right? I'm finding one point here, one point is here, and another point is here, and I'm reading these values of QA and H, and we know that for the first point, what will be the value here? So that is 10, 11, 12, and that will be 13, right? And then for QA, it is this one. Let me just calculate. It is 200, and then that is 250, right? It's directly there, 250. So the first point is 13, 250, right? That is H and H1 and QA1. The second one here, this point, what will the value? What will be the value of this? This is the 100. No. See, we have made mistake here. That is not 13. That is 10. That is 20. That is 30. Okay, so that is 40. So it is not this one. It is basically 40. So it is 40, 250. And what will happen for this point? It is 40, 50, 60, 70, 80, 90. So that is 90. So the next point is 90, and that value, what will be the value of this one? This is 350. That is 400. So that is 360 and 370. So that is 370. So from these 2 points, we can calculate n, right? We know the equation, log of QA1 divided by QA2 divided by log H1 divided by H2. If we apply that, so what will happen? So we know that the value, so log, it will be 250 divided by 370, and then log 40 divided by 90. So let me calculate that. So it will be log 250 divided by 370 divided by log 40 divided by 90. Okay, and then I'm getting the value of n is 0.483, right? It should be, the theoretically it is 0.5, so we are getting 0.483. It's fantastic, we got it. So now we have to calculate the value of C, right? We have the equation QA is equal to C is to the power 0.483. So we can use this, or we can use that one as well. So I'm using that 250, the first point. 250 is equal to C is unknown, and then 40 to the power 0.483, and what will be the value of C? So 40 to the power this, and we have 250 divided by that, and then we'll have a 42.01, the value of C. So we have the calibrated equation, right? We can write the calibrated equation here, that okay, this is the calibrated equation I have for this experiment. QA is equal to 42.01, and h to the power what? H to the power 0.483. So that is my equation. If you write this equation right on the orifice meter, then you can measure that head, actual head, after correcting that head, and you can use that head here, and you can calculate QA, the actual flow rate. But you don't need to calculate every time. Other than calculating this value using calculator, what you can do, you can measure, you can use different values of H, okay, actual head like 5, like 10 or 20 or even 100, and then we'll get actual value. Then you can plot it, right? You can plot. Then you can plot graph paper, right? Like this. It will be like this. If you plot H here and if you plot QA, this will be normal graph paper. Then we'll have a line like this curve, and then you can calculate. For example, we need to calculate the value of QA at 50. Okay, then you can read from the graph directly. You don't need to calculate using calculator. And if you have another point, another reading, you can calculate. So you can prepare this graph, and we can paste this graph on this orifice meter or on the tank. Then someone will measure the head, actual head, and then they will read from this graph. So that is another way. So this is the calibration curve for that Venturi, for that orifice meter, right? The same way we did for the Venturi meter. Then let me just calculate for velocity. So we can even do the same calculation for the velocity, actual velocity. So I plotted here actual velocity here along y-axis and same actual head, because we know the equation, right? It is VA is equal to C1 and H to the power M. So from this graph, we can even measure this point and we can measure this one. So what we can get it, right? So it is 20, 30, 40, and that is 50, right? So first point is 50, and this what will be the value of this one? This is 100, 200, that is 300. Okay, so we have 50 and we have 300. And what will be the second point? That is exactly 100. Okay, and what is the value of this one? This is 300, 400, and there is 500, but it is in between 450. So 440, we can measure 440. We don't have any point that is on the line, so we can assume that way it's less than 500, even 4, yeah, and then more than 400. So this way, so we can calculate the slope M again using the same formula, like log VA1. Now it will be VA1 and VA2 divided by log H1 divided by log H2. Can apply that, and then we'll have log of 300 divided by 440 and divided by log 50 divided by 100. Let me calculate it again. It is log 300 divided by 440 divided by log 50 divided by 100. Okay, so what we have the value of M is 0.55. So that is the value of M. It is even more than 0.5. The actual value is 0.5. So let me calculate, because we have VA is equal to C is to the power 0.55. So we can calculate C1 here. So VA, I'm taking the first point, 300 is equal to C1 is unknown, and 50 to the power 0.55. Okay, 50 to the power 0.55, and we have 300 divided by that answer. So we have 34.54. So we can write our calibration equation here. That okay, we have the equation actual velocity is 34.54 and H to the power 0.55. This is the calibration equation for our actual velocity. So this is how we can calibrate any device, right? So the main objective of the calibration is to measure the actual parameter, actual velocity or actual flow rate. So for this case, we measured both, right? Actual velocity and actual flow rate. So that is the orifice. It is pretty simple. If we have an opening, small opening, right, and then you can measure the actual head over this opening, and then you can even use this equation to calculate the actual flow rate and actual velocity as well. So this is pretty simple equation, and it is pretty effective to measure the flow rate, or in order to measure the control the head of a reservoir that is effective, very effective. So we can use orifice meter. So next we'll see another device. Okay, so this is how we plotted, we calculated, and there are some, yeah. So we already maybe covered this one, that what are the coefficient of velocity? You know, it is the ratio of the actual velocity to the theoretical velocity, and coefficient of contraction. It is also the ratio of the area at vena contracta to the ratio of the opening or orifice, and coefficient of discharge. It is same, the ratio of the actual velocity to the ratio of the actual discharge to the theoretical discharge, and on what factor do this coefficient depends. Definitely it's the opening, right? Opening, it should be rounded opening or it should be any thicker opening. So depends on that one. And if your hole is more, then it will be different. So what are the average values of this coefficient for sharp crested wheel? It is not that big, it is around 60%. So you can find it using online search or from your book. It is already this. These are this thing. And what is submerged orifice? Right, so the same values for this orifice, like 50%, 60%, or 70%. So that's the value, exact value I can't remember. You can find that values from the book. So the submerged orifice will be like that. If you have a tank, and if you have opening here, right? If you have opening here, but this tank is, we have another tank, and we have water. That is the submerged orifice, right? Water will flow like that. We have this opening, and water will flow, and then it is submerged. We have head here, so that is called submerged orifice. So definitely it is different than the orifice we saw. The previously it was directly flowing to the air, but now it is flowing right under the water. It is submerged. That's why it's called submerged orifice. Right. So why the number 3? Why is the actual discharge through an orifice right, is less than the theoretical? Definitely it's because of the friction, right? Definitely we can't even neutralize that thickness. We can make it like a line, but we can't neutralize that one. So because of the frictional effect and the unsteady head, because it is very difficult to maintain this head constant, and considering all this, because the fluid is not even incompressible, it is even, it is incompressible, but it is not non-viscous. It is also a viscous fluid, because these are the real fluid. So that's why there will be some losses, and because of this loss, that flow rate is less than theoretical. Okay, and write different types of orifice and their coefficient. Yeah, there are different types of orifice: rounded orifice, sharp crested orifice, right? So they have different coefficient. You can find that one, and different vena contracta, and why why does it form vena contracta, right? We know that if we have any opening and we have flow, right, it's happening, streamlines are converging, and then it's just flowing. It's converging and then it's flowing. So we have an area here that is minimum, right? It's even converging. That is basically 0.5 D, since that is the D. So because of this narrow opening and head, streamlines, definitely when it have a path to flow, it is just converges at first. And when it's converging, because of the momentum, it is even converging after this, right? After passing this opening. And then it is still, it's continue to converge. And because of this continue to converge on the momentum, and then at a certain distance, that is 0.5 D, the minimum cross-sectional area, right, will have. So that is called vena contracta, where the cross-sectional area of the jet is minimum, and that area is located at a distance of 0.5 times the diameter of the opening. Okay, so that is that. And then will the value of CV be different for sharp edged or rounded orifice? It may be different, but sometimes it may not be different. It may be same. So that's the thing. It won't even affect. Okay, it won't affect the whether this orifice is sharp edged or rounded. It is same. Sharp and round it's the same, right? If it is rounded and if it is sharp, then it will be the same. Otherwise, definitely, if it is sharp and it is round, but it has a thickness, then it will be different. So these are the equations, and these are the questions, the answer I can think of right now. And these are the calculations I just show you. Okay, and that is the graph and that is the way we can calibrate any device, right? So you can even, calibrate your own model. Means this type of prototype model, if you have any Orifice meter or anything, you can do this using any other computer modeling to see what is actually happening. You can see the streamline and you can see the jet, or you can use your device in the laboratory, or you can even build a new one by yourself. So for building any flow measuring device, we can apply the energy equation, Bernoulli's equation. So that's what is fluid mechanics. It is a very basic level course. So we need to understand how can we calibrate any flow measuring device. In reality, we have to use different types of devices, and we have to know how to calibrate. If we take some results, if we take some readings, and if we want to calibrate our device, we need to plot this way or that way. So that's the basic way, and you'll be able to even plot on a log graph paper. You'll be familiar, right, with this log graph paper. Previously, you may not have idea about that one, and we'll plot this type of plotting every day, right, for every experiment, literally for every experiment. So having said that, I'm gonna finish here. So if you have any query or any difficulty, you can ask your instructor, or you can search for any answer, or you can make any comment on the comment box if I need to improve any part of the tutorial, right? If you have any problem understanding the basics, because what I try to say, I try to explain more, and I try to show all these equations, even though all these are written in the manual or written in the book. But other than doing that, I just try to derive how it's been derived, right? So then if you know how to derive the equation and how to form the main or the final equation, then you can understand what is actually happening, what is the logic behind this, and what are the assumptions, right, we have made to derive this equation. So that's why I do the thing every time. And if you do the same thing repeatedly, then you'll be familiar with that one, and you can remember that thing. So practice writing and deriving that equation. So thank you very much. Thank you for watching this time. See you next time and in the next tutorial. So stay safe until then.